So last section we're going to look at this week is 3.2. I might choose to only look at pieces of this. Well, we'll kind of see as we go. But there are three things in the section, if we cover all of it. Continuity, intermediate value theorem, and what's called end behavior. So we'll talk about each one of them. So I don't remember if it was in here yesterday, or it might have been one of my other classes where there was a graph that somebody tried to draw on their calculator. Was it you? Yeah, and it connected it.
Yeah.
So most calculators assume that you want graphs to be connected, okay, like Quinn's did. Well, there's a newer feature in some of the calculators that will say, well, maybe my graph isn't supposed to be connected. Older calculators, no matter what you did, anything you drew on the screen, it would try to connect it. So I'm trying to think of the exact problem we had yesterday. Maybe we had something like this. No, it wasn't that. Let's try it like that. Yeah, maybe it was something like that. I don't remember exactly. But the point is, it's trying to connect it and it shouldn't. So on newer calculators, if you press second format, you can go to this detect asymptotes. You'll notice it draws it a little bit slower, but it draws it correctly. There should not be a connection between those two pieces. And whether or not you can draw a graph that is connected or not connected, that has a name. So I'm going to tell you what it's called when you can draw a graph, basically without ever lifting your pencil to do it. So I just graphed something like that. 1 over x minus 3. Well, I did 1 over x plus 3. Same idea. If you graph that, you could not do it without lifting up your pencil. You'd have to draw one section, lift, put it back down, and then draw the next section. That's different than sketching, say, like a parabola. Parabola, put down what I'm drawing with, draw the whole thing, and then lift. I never had to lift it in the middle of drawing. This one you did. So that was, let's put that one right there. So that was that one. This other one, I don't know if we've studied it a lot, but I just want you to look at it. You don't have to know how to draw this one. This is called the integer function. Could you draw that without lifting your pencil? No, that one you got to lift it a bunch of times. It's almost like a series of steps. Okay? And another name for this is called a step function. But the point here is you cannot trace this graph without lifting your pencil at the end of every step. Now, how about this one? X squared. That's a quadratic. It would be a parabola. Could you trace that one without lifting your pencil? Yes. So the idea is if you have to lift your pencil, that means something. If you don't, well, then we can call it something else. And that's called continuity, okay, or continuous. So we can say that a graph is continuous over a certain section. Sometimes the whole graph isn't continuous, but maybe you can find a section that is. Like if I had a graph like this, no, the whole thing isn't continuous, but maybe I could trace from like 1 to 4, and that small section is continuous. Or maybe I could find tons of other sections that are continuous. But the whole thing is continuous. All right? So if you can find a section that you can start at, and you can stop at, and you can trace between the starting point and the stopping point without ever lifting your pencil, then what you just found is called a continuous interval. You started somewhere, and you stopped somewhere, and you never had to lift your pencil to trace. That's called a continuous interval. Some graphs are continuous everywhere, like a parabola. If I give you a parabola, and you tell me somewhere to start, and you tell me somewhere to stop, I don't care where you tell me to start and stop. I will never have to lift my pencil when I trace a parabola, no matter where you start, no matter where you stop. For this graph, that's not true. If you start at a certain point and you end at a certain point, you could give me values that I would have to lift my pencil if you said, trace between this number and that number. It is possible you give me a section that is not continuous. It's also possible you give me one that is continuous. If you try to trace from a starting point to a stopping point, and you had to lift your pencil to do it, then that's called a discontinuous interval. That's called discontinuous. So, as I said before, sometimes this isn't like an all or nothing thing. Maybe you can find a small section that's continuous. Maybe not the entire thing, but maybe part of it. So, what we're going to do is we're going to draw the graph of 1 over x. And I want to name 2 intervals that are continuous, meaning I can start and stop somewhere without lifting my pencil. And then I want to name 2 intervals that are discontinuous, meaning if you told me to go from a start to a stop, I couldn't do it without lifting the pencil and putting it back down somewhere else. So first thing is, to get an idea of the 2 intervals, we need a sketch of 1 over x so we can see it, and then go from there. Okay, so let's put in 1 over x, graph, and let's put the picture over here. So let's start with 2 intervals that are continuous. Could somebody give me a number that I could start at and a number that I could stop at? And if I trace between those 2 numbers on that graph, I would never have to lift my pencil to do it. Declan?
It's like negative 0, not 0.
Okay, so we could have negative infinity up to 0, not including it. Technically, that would be a continuous interval, but you could never possibly trace it because it's an interval that goes on forever. So this is an unbounded interval, but technically it is continuous. Now, could somebody give me a bounded interval that's continuous? An actual start and an actual stop, and I could do it right now. Yep?
-6 to -2.
So -6 to -2. Doesn't really matter if you include the -6 and include the -2. You could, you couldn't. But the point is, I could start at -6. I could go to -2. And I just traced between -6 and -2 without lifting my pencil. So there's 2 intervals that are continuous. Now, let's do discontinuous. Could somebody give me a value that I could start at and stop at? But if I tried to do that, I have to lift my pencil to do it. Yeah?
-1 to 1.
-1 to 1. I cannot trace from this point to that point without lifting my pencil. I have to stay on the graph. How about another interval that would be discontinuous? Yeah?
-2 to -2.
-2 to, yeah, -2 to 2, or,
That's what I meant. Wait, did I say negative twice?
I don't know.
Yeah.
Maybe, yeah.
Yeah, I meant -2.
Alright, we'll check the recording.
Yeah.
So -2 to 2. Basically, anytime you try to pass through what number, you're going to have to lift your pencil in this problem. Laura? 0. 0 is the problem. If you try to go through the number 0, you're going to have to lift your pencil to do it. If you don't go through the number 0, then you're okay. So, what this is called right here, this place where we have to lift our pencil to continue somewhere else, that is called a discontinuity. It doesn't have continuity, it's a discontinuity. It's a place where you have to lift to keep drawing. And there's 3 different ways you can get a discontinuity in a graph. Let's go back and look at this problem for 1 second. That's what I just drew. What value are you not allowed to fill in for x here? Yep. 0. Why? Right, because you can't divide by 0. So one way you can get a discontinuity in a graph is if you try to divide by 0. That's called an undefined value. So if you have a graph with a variable in the bottom, whatever number you could plug into that variable that would make it 0, that is a discontinuity. That's called an undefined value. Now, another place that you can get discontinuities is not an undefined value, but it's called a break. And when I showed you guys this series of steps, those are called breaks. They're not undefined. The reason they're not undefined is because we didn't talk about it a lot, but what the integer function does is it basically rounds a number off to the biggest integer that it can that's less than the number you plug in. So like if you plug in 3.2 for x, what's the biggest integer you can think of that's less than 3.2? Yeah?
3.1.
Integer. Has to be an integer. Yeah? I can think of an integer that's bigger than 2 but less than 3.2. Yeah? 3. 3 is the biggest integer that's less than that number. How about 3.5? What's the biggest integer that's less than 3.5? Yeah? 3. How about 3.9? Yeah? 3. So you notice it just stays at the same value for a while. Now, what about if I said 4? What's the biggest integer that's less than or equal to 4? 4. So all of a sudden, it jumps from 3 to 4. I didn't plug something in and get an undefined answer. It's just the way that this function rounds things off. It causes breaks in the graph. Okay? Both of these are easy to see. You can very easily see if you have breaks. You can very easily see if you have an undefined value where the graph kind of curves in opposite directions. The third way that you can get a discontinuity, you cannot see on a graph. And that would be this one. Let's type that in and see what it looks like. So we're going to put in x squared plus 3x plus 2, and we're going to divide by x plus 2. And I'm going to do zoom 6. If you look at that graph, does it look like I had to lift my pencil at any point when I drew that? No. doesn't look like I did. But we know by looking at that, there is a number that you cannot use for x in this problem. What number are you not allowed to use? Yeah. You can't use -2. And if you try to use -2, the calculator will tell you that it's an error, but you can't see it. And the reason you can't see it is because this is what we call a hole. A hole is infinitely small. It's extremely small. The hole is right there. That's how you would sketch this graph. The calculator can't do that. It can't show you that there's a hole. But you can tell there's a hole because let's take the numerator and factor it. If you factor x squared plus 3x plus 2, what does it factor into? Oh, -2. Thank you.
Yeah.
I could tell. Not +2. The hole's at -2. So what does x squared plus 3x plus 2 factor as? Yeah?
X plus 2, x plus 1.
X plus 2, x plus 1. What do you notice in the numerator and the denominator? What do they both have? Yeah?
Both have 2's. X plus 2.
They both have an x plus 2. That's when you get a hole in a graph. If there's a value that would cause you to divide by 0, but you have a common factor in the top and the bottom, that will cause a hole. If you have a value that causes you to divide by 0, and there isn't a common factor in the top and in the bottom, that's when you get something that's very obvious to see, where it curves in opposite directions. So, if I took this problem and let's go back here for a second. Change the numerator to just be, instead of plus 2, just make it plus 2.1. So I just barely changed it. I changed it from 2 to 2.1. But the point is, now it does not factor as x plus 2, x plus 1. So that means there will not be a common factor in the numerator and denominator. Watch how just by changing that to 2.1, it looks completely different. Okay, so we get something that kind of looks the same on the ends, but in the middle, it's very, very obvious now that there's a discontinuity. So this last one, having a hole, it's basically like having an undefined value. The first one and the third one, both are dividing by 0. In the first case, you're dividing by 0. There's no common factor in the top. In this case, you're dividing by 0, but there is a common factor, and that causes a hole. Okay, so any questions on when you get a hole in a graph? Yep.
What if there's 2 common factors in the top? Like it's x plus 2 and x plus 2.
So if you had 2 common factors, let's just actually try it and see what happens. So x plus 2. So basically you said like x plus 2 squared, right? X plus 2, x plus 2. And if we divide that by x plus 2, we still get a hole. Yep, still get a hole. And if you don't believe me that there's a hole, try to go to -2. And when you do, the calculator is like, what? What do I do for y? Because it can't do it. Yep. So anytime you have a common factor, even if it's more than 1, you still get a hole.
Sorry, so when you went to like that chart that had like the error for -2, how do you actually get there?
I press second and then I press graph. Yep. Now, polynomials. Okay, that's what we started to talk a little bit about yesterday. Polynomials never have square roots in them, and polynomials never have variables in the bottom of a fraction. So because of that, every single polynomial is continuous all of the time. Think of a parabola. You can't give me a parabola and that I would ever have to lift my pencil to draw. It's impossible. Every single parabola that exists can be drawn from anywhere to anywhere without ever lifting your pencil. And if you have something that can be drawn all of the time without lifting your pencil, that's called a continuous function. So the idea of a continuous function is not just a small section is continuous, but the entire thing is continuous. You can't find a section that's discontinuous. It's impossible. So any question on that idea? A continuous function. Okay. So that's the first part. Okay, so I remember I said there were 3 parts. Continuity was the first one. We're gonna skip the second one. We're just gonna do the last one. So I want to think for a second about continuous. Okay, some things like in real life are continuous and some things are not. For example, if I put water in a pan, right, and the water is at room temperature. Let's say the water is at 70 degrees, and I heat the water all the way up to boiling in Fahrenheit, 212. As the water heats up, what temperatures will it go through as it goes from 70 to 212? Or how many different temperatures will it go through? Yeah?
Every single one between 70 and 212.
And how many temperatures are there between 70 and 212? Yeah? 42? That's the answer? 42 different temperatures. How'd you get that?
You just, basically, all I did was I just subtracted 212, or 70 from 212, and that's over the temperature it goes through.
Okay, so I see what you did there. But if you subtract 70 from 212, that would give you how much? It would be more than 42. Yeah? So there's only 142 temperatures between those two. What about 70.3? Yeah? There's an infinite number of temperatures between those two temperatures. There's an infinite number of temperatures between 70 and 71. Infinitely many. So as you heat water from 70 to 212, that's called a continuous process. And you will go through every single possible temperature between the two. So will there be a moment when your water is exactly 90.74 degrees? Yes. There will be a moment when it is exactly that temperature. You can't skip a temperature as you're heating. That's impossible. So that's called continuous. And the idea is I will go through every intermediate value between 70 and 212. I have to. I can't skip. If I'm driving to a city and I watch let's say I had a GPS and it's keeping track of how far I am from the city that I'm driving to. Maybe I start at 60 miles away, and by the time I'm done, I'm going to be at the city and I hit 0 miles away. Your distance shrinking as you travel to the city. would that be continuous? Or would it not be continuous? What do you think? That's continuous. There is a time when you were exactly 50.2 miles away, or 49.3716. You're going to go through every possible distance from 60 miles away all the way down to 0 miles away. That's continuous. Now, let's say I count the number of people in the room. 1, 2, 3, 4, 5, 6, all the way up to 25. Counting. Is that continuous? You think, Declan?
No.
No. If I count from 1 to 25, I'm not counting every single number that exists between 1 and 25. I'm not counting 1.6, 1.8, 2.417. I didn't count any of those. I skipped. So that's not continuous. And the idea is if you have something that is continuous, you will hit every number or every what they call intermediate value between the start and the stop. If it's not continuous, then you won't. Like counting is not continuous. All right, so that's roughly the idea of the intermediate value theorem. It only applies to something that is continuous. That's what it's applied to. Any question on that? Okay. So the last thing we're going to look at is what's called end behavior. End behavior looks at what's happening to a graph on the left and the right side. Way on the left and on the right. It doesn't care what's happening in the middle. So if you have a graph like this, maybe it goes up, it goes down, it goes up, it goes down, and then it goes back up. If I was going to describe the end behavior of that graph I just drew, I would say that it's down on the left and it's up on the right. That's called the end behavior. Does it take little twists and turns in the middle? Sure. Do we care about that when we're talking about end behavior? No. It's just what's happening on the left and what's on the right. And there's really only 4 different options for end behavior. You can either have something that's like a parabola, that would be up, up. You could flip the parabola, and it would be down, down. Or you could have one of each. One side's down, one side's up, or one side's up and one side's down. But those are the only 4 different types of end behavior you can have. And I'll write that down. So let's look at one way we could write end behavior, and then I'll show you another way. Let's graph y equals x cubed. So if you have anything else in there, you just get rid of it. And let's see what y equals x cubed looks like. Okay. So that's what it looks like. To describe the end behavior, you have to tell me what's happening to the y values on the left side. Are they going up or are they going down? What's happening to the y values on the right side? Do they go up or do they go down? So what's happening to the y values as you keep traveling to the left in this graph? Yeah.
They're decreasing.
They're decreasing. So on the left-hand side, the y values are going down. How about on the right-hand side? Yeah.
They're going up.
They're going up. So that's one way you could see end behavior described. It kind of looks like a coordinate, but you put arrows inside it. And here's the other way. This part right here can be described by what I'm about to write right there. Let me read this exactly how it's written, and then I'll try to simplify it. So this is pronounced the limit of f of x as x approaches infinity. That's very formally how you say it. The limit of f of x as x approaches infinity. Now, when we write f of x, that's another name for what letter? Y. So what this is really saying is, what is happening to the y value as you head to the right? Infinity is to the right. So what is happening to the y value as you head to the right on the x-axis? It goes up, and what does it approach? It approaches infinity. So as you continue heading further and further to the right, the y value continues to go up and up and up. So that's infinity. This part is describing what we're going to write right here. Formally, if you read that, it says, what is the limit of f of x as x approaches negative infinity? Breaking it down and making it a little simpler, what's happening to the y value as you head to the left? Negative infinity is to the left. So what happens to the y value as I head to negative infinity? Yeah? I approach negative infinity. So the four options you would have here are both infinities, both negative infinities, one positive, one negative, or one negative, one positive. Those are the four different options you could have.
So what question do you like to send include? And then what would you put for the answer? Like those two in the box right there?
It just depends which way they ask you to write it. If they say to write your answer in what's called limit notation, these two on the right are limit notation. This way on the left, I don't really know if it has a name. It might just say write your answer using arrows. But this is specifically called limit notation because of the word limit. And these are the four types of end behaviors. Both up, both down, down, up, down. With polynomials, there is nothing else that can happen. So let's graph this one and see if we can identify the end behavior for y equals x to the fourth. Eventually, you're not going to have to graph it to figure this out. I can tell you the end behavior of y equals x to the fourth is up, up. And the way I know that is because you can always put a 1 there if you want. I can look at this number, and I can look at that number. And that tells me everything I need to know. The fact that this is an even exponent, and the fact that that number in front is a positive. Let's see. Let's graph it, just to double check. But, as I said, y equals x to the fourth, end behavior is up, up. So one way we could write it is just like that. Or, if you wanted to write it in limit notation, you would take what we had right here, and it's up on the left, up on the right. You could write it just like that. As you head to the right, it goes up. As you head to the left, it goes up. This would be the answer in limit notation. I'm going to fix it and put it back the way it was to this point. But that's what it would be. Does anybody have a guess what y equals negative x to the fourth will be? If you think about having a negative in front, remember what that does to something? Yeah?
Maybe down, down.
That would be a down, down. And if you wanted to describe that in limit notation, you'd take what we had right here. Down, down. That's how you would do it. Down on the right, down on the left. So again, the key is, what is the highest exponent, and what is the number that's in front? Is it a positive or a negative? If you know those two things, we can figure out any end behavior. This represents the highest degree term in your problem. So if you had something like 3x to the 4th minus 8x squared plus 2x plus 1, and you're like, well, wait a minute, which term do I look at? You look at this one. The terms with lower exponents don't really matter. So we just ignore them. The only thing that matters is the term with the highest exponent. If your highest exponent is even, and the number in front is a positive, we can look that up. Even exponent, and the number in front is greater than 0, that's a positive. This is an up. If the highest exponent is an even, and the number in front is less than 0, that's a down. So whenever you have an even exponent, it's either both up or both down. And it's easy to remember. Negative is down, positive is up. The odd one can be a little tricky because you have one down and one up. So you have to remember which one is which. If you had something like 8x cubed, positive, odd. Odd, positive is going to look like this. That's a down up. If you have negative 8x cubed, that's going to be up, down. So any questions on the two numbers you focus on to figure out the end behavior? Okay. I think this is the last one. So I already told you this, but the leading term, okay, if you have a bunch of them, 8x cubed, 5x squared, plus 3x, plus 6. The leading term is the one with the highest degree. This is going to control the end behavior. It controls the whole polynomial. So what about the negative 5x squared plus 3x plus 6? You don't need it. Would it control little details? Sure, absolutely. There'd be little twists and turns you could see. But none of this matters when we're finding the end behavior. So because the leading term predicts the end behavior, we call that leading term the end behavior model. So if you've got some really long polynomial, the only thing you have to look at is the very first term. This term alone is called the end behavior model. From now on, we'll abbreviate it EBM. Right, and we'll finish up by finding an EBM and graphing it, and that'll be it. Okay, let's try an example of finding an EBM. There's my polynomial, And first, could anybody tell me what the EBM would be for f of x? Yep.
2x.
Yep. 2x cubed. That's the EBM. So let's graph it. I want to graph the original, and then I want to graph the EBM. The idea is they should look the same. You might say, well, what about all the other stuff? It's not going to really matter if you zoom out far enough. The EBM gives you a big picture. So if you zoom out enough, the EBM in the original problem should look pretty close. So let's try graphing it. And first, they tell me to do a window of -8 to 8 and -100 to 100. Okay, so type them both in. Let's do -8 to 8 and -100 to 100. That's not really zoomed out that far. -8 to 8, that's even zoomed in more than the standard window. So let's see how the EBM and the original problem compare. That's the original problem. 2x cubed minus 7x squared, all that stuff. There's the EBM. Do they look identical? Like, do they look like, when I say identical, I mean like they're almost exactly on top of each other. No, they're not that close. But that's because we're zoomed in quite a bit. So let's keep the same graph, but now let's zoom out -100 to 100 and -40 to 40. -40, wait a minute, no. -40 to 40 and -10,000 to 10,000. I messed that up. -40 to 40 and -10,000 to 10,000. Now this is zoomed pretty far out. If we found the right EBM, it should look like it's almost exactly on top of the original. Let's see. Or it should look close. It should look really close. Okay. How close do those two look? They're pretty close. And if I zoomed out more, it would look even better. So the idea is this graph basically looks just like that if you zoom out enough. This predicts what the whole thing is going to look like. I mean, that's a pretty good prediction. It's almost the same thing. Does it take little twists and turns in here? Absolutely. If you zoom back in, you'll see them. But that's not what we were interested in. And I'm not going to graph it, but what would the EBM be for example 7? Yeah.
-0.5x raised to the 4th.
-0.5x raised to the 4th, and would that be up, up, down, down, or one of each? That's a down, down. Even exponent, negative number in front. Down, down. And that's it. Put up the homework. What I will do is I'm going to put a list of topics up. I've got about 7 minutes, so I might be able to get the whole list of topics up before the end of class. But if not, I will make sure it's in the video.